Hi, I'm Zor. Welcome to Zor Education. We were talking about systems of equations in general, and then in particular systems of linear equations. Well, this is kind of boring stuff because everybody knows how to solve them. It's no big deal really. We have certain algorithm which always works. Like, for instance, you do the substitution from one equation to another, you get another system of linear equations of a lesser number of variables and lesser number of equations, and then etc. etc. You step by step you reduce it down to zero, and then you solve the linear equation. No big deal. It's time to complicate your life a little bit. So after we were learning about linear equations with one variable, we switched to quadratic equation and then higher order equations. Same thing with systems of equations. We have learned about linear systems, and now we will go into quadratic systems. So, a couple of words related to definition, theory, etc. First of all, to define what is a quadratic system of quadratic equations, we will have to familiarize ourselves with the concept of univariate and multivariate polynomials. Now, univariate polynomial is something which you definitely know. It's something which looks like this. It's a function of one variable, which is x, in certain powers multiplied by certain constants, usually real numbers. Well, sometimes complex, but it's really very, very rare. So it's usually real numbers, and then summed together. So this is a function of one variable, and this particular function is a polynomial of nth degree, because we assume that a0 is not equal to 0, so the maximum power x is raised into is n. Now, this is called, as I was saying, univariable polynomial because it has only one variable, x. I would like to extend this definition to multivariate polynomials. Now, what is this? Well, it's multivariate. It means there are multiple variables which are supposed to participate in this polynomial. Now, in what way? In some way it's similar, but instead of one variable x, we have multiple variables. So, let's say you have x1 to some power I1 times x2 to some power I2, etc. xn to power in. Now, this term will be used instead of this one, with some powers which each variable x1, x2, etc., xn is raised into. So, this is one single element from which we will construct the multivariate polynomial. So we have to multiply this particular element to some constant, which I would put something like I1, I2, etc. Doesn't really matter what kind of indices I'm using. So we multiply it, and then we add another term which looks exactly like this, except these n variables will be in different, raised to different powers. So let's say it would be xi j1, x2 j2, etc., xn jn. Again multiplied by certain coefficient a, j, whatever. So sum of these with these particular variables raised into different powers is a polynomial which we can call multivariate polynomial. Just as an example, let's say I have only two variables, x1 and x2. Then an example would be x1 squared times x2 plus 3x2 plus 4x1 x2 to the third power. Something like this. Doesn't really matter. So the combination of product of variables raised into certain powers multiplied by constants, in this case the constant is 1 obviously, and summed together. So anything which looks like this is a multivariate polynomial. Now, it does make sense just to kind of to order things in your mind, to really consider the polynomial of this type in a sequence of increasing or decreasing combined power of all the variables. Now, what's the combined power? Combined power in this case is 2 plus 1, which is 3. Combined power of this is 1. Combined power of this is 1 plus 3. x1 to the first degree and x2 to the third degree, which is 4. So it makes sense to rewrite this as 4x1 x2 cubed plus x1 square x2 plus 3x2 in the order of decreasing of the combined power. It's just to make it a little bit better, a little bit more orderly, if you wish. So the maximum combined power will be in the first place, then it will be next less than that, etc., etc. Now, if the combined power, the maximum combined power is equal to 2, then this particular multivariate polynomial will be called quadratic, which obviously is reasonable, I would say. So let's just talk about examples of quadratic polynomials, multivariate polynomials. Well, for instance, x1 squared plus x2 squared. This is quadratic because the maximum power, combined power, is 2. Now, x1, x2 plus x1 plus x2. This is also a quadratic polynomial because the maximum power is 1 plus 1, which is 2. These are less than that. So the maximum power is 2, so this is quadratic polynomial. And obviously there are many other examples which you understand. Now, in this particular case, I'm using x1 and x2 as variables. I can as well use x and y and z and u and v and whatever other letters, doesn't really matter. So this is also a quadratic polynomial where a, b, and c are constants and u and v are variables. Because in this case, the combined power of this particular term is 1 plus 1, which is 2, so it's a quadratic polynomial, multivariate, which depends on two variables, u and v. All right, so that's all about the theory of what is quadratic polynomial. Now, obviously, the system of quadratic equations is a system, which means more than one equation. Each one of them contains quadratic or less than quadratic, which is actually linear, polynomial. But at least one equation in the system must contain the quadratic polynomial for the whole system to be quadratic. So this system is quadratic. Why? Because one of the polynomials on the left of the equations is quadratic. The second one happens to be linear. So again, the system of quadratic equations is a system of equations with the left part containing multivariate polynomials, at least one of them of the second degree, and there is no more than second degree polynomial. So there is no third degree or fourth degree, etc. So it's either second degree or the first degree multivariate polynomial. So that's the definition. All right, so I have a couple of examples here, and I will just put it on the board. Okay, this is the first system which I suggest as an example. Something like this. This is a system of 3 equations. It's a quadratic system because each one of these equations is a multivariate polynomial on the left of no more than the second degree. And we do have actually second degree polynomials on the left as well. One is a linear. So this is an example of a system which I'm talking about. Now, would be interesting to talk about solutions, obviously, right? It's one thing to present a system of equations, another is to solve it. And this is actually much more problematic in case of quadratic systems than in case of linear. In case of linear system, you can just learn how to solve the equation. Well, you just, for instance, using the substitution method. You take the first equation, the second equation, etc., substitute, no problem. There is no general methodology to solve quadratic equations. Why? Because let's say you want to do it using the substitution method. Well, look at this. You can actually find out what z, let's say, is from this. Z is minus square, z squared is minus xy, so z is square root of minus xy. And it can be actually plus or minus. Then substitute it into this, and what will you have? You will not have an equation which can be easily solved, or to this. I mean, it's not easy. There is no general solution, general approach, general algorithm how to solve the quadratic equations. So, it's your ingenuity, actually, which must really help you to find certain peculiarity in the system which will allow you to solve. Well, except one case. One case is, what if in my system I have one equation of the second degree like this one, and other equations, all other equations, are linear. Something like this. In this case, the situation is easier and it can be actually solved like basically algorithmically. I mean, there is a way to do it. How to do it? Well, take a look at the linear equations. Now, if you have a system of n equations with n variables, n minus one of them are linear. Now, let's assume that you just take one particular variable out of these 3 and as a base, and just consider it's given. And you can solve this system of 2 equations with 3 variables as basically 2 variables in terms of the third one. So let's consider that z is something which is known to you. Then basically you can consider this as a system x plus y equals 5 minus z, right? This is the first one. And x minus y equals 5 plus z. Now, if z is known, you can solve this equation of 2 variables, but it will be obviously in terms of z. So x will be some kind of a linear function, linear, that's important, of z, and y should be linear function of z. Well, in this particular case, the easiest way is just to add them together. It will be 2x 10, so x is equal to 5. It's a constant actually, but if you will subtract from this, you subtract this, you will have 2y equals to minus 2z, so y is equal to minus z, right? So this is a solution, but a solution in terms of z. Now, considering this, you can substitute both x and y into this first equation, which is of a second degree. it's a polynomial of the second degree, real quadratic polynomial. But we know that this is a polynomial of second degree. So if anything, all these variables are described as linear functions of z, then I will, as a result, have a quadratic equation of z. All right? So let's write it down. Instead of x, I will put 5, so it's 25. Plus xy, it's x times, so it's minus 5z xy. So it's minus 5z plus xz, xz, which is 5z, equals to 8. All right. In this case, I have a contradictory equations because I just made it up. I didn't really think about what kind of equation I said. So this is a system of equation which doesn't really have a solution because I have 25 equals to 8. However, if I were somehow differently, let's say this is instead of yz xz, what this is yz, for instance. I don't know what happens. Let's see. In this case, instead of 5z, I will have plus yz is minus z squared, right? So it's minus z squared. Now, what happens now? Is this an equation which does have solutions? Well, it's z squared plus 5z minus, 17, right? Z squared plus 5, 17, minus 17, right. And this is an equation which does have a solution. Z is equal to 2 minus 5 plus minus 25 plus 34, 68, something like this. So whatever this is, this gives me z, and then since x is equal to 5 and y is equal to minus z, I have the solution for everything. So in this particular case, when the system contains only one real quadratic equation and all others are linear, then we can actually basically have a procedure which will definitely give you some result. You solve these, which are linear, in terms for all variables instead of one, and then substitute. In all other cases, it's much more difficult. It needs some ingenuity, as I was saying, and the only way to approach learning something about this system of equations is, well, very simple. You solve as many as you can. You listen to lectures if I'm presenting something, you read whatever you can read, and the more practice you have in solving different equations, the more approaches you will have in your mind, and the next one will be probably easier. Because there are only a certain number of different techniques which you can use, and obviously people who are creating systems of quadratic equations for you are also kind of restricted to a certain number of rules and techniques, etc. So the more you solve them, the easier you will feel. Now, in my particular case, I just want to relate you to the previous lecture which I had about relativity, which I included into the systems of linear equations, and for one particular reason, because it's actually of this type I was just mentioning. One particular equation was a quadratic equation, but the rest, there are 4 equations altogether. So one is quadratic and the 3 were linear. So I was basically using this approach which I was just talking about to solve linear equations in terms of one particular variable. The fourth variable, if you wish, or the first variable, and then the second, the third, and the fourth are in terms of the first. And then substitute it into the quadratic equation, basically getting the solution. So let me just very briefly tell you what it is, since this is a good example. This is what I've had in this lecture about relativity. And I will try to do it very quickly. For details, I do refer you to this lecture. This is an example of the system of 4 equations with 4 variables, P, Q, R, and S. Now, C and V are constants. Now, as you see, this, and this are linear equations where P, Q, and R, and S all are linearly related to each other. And only this one is really quadratic equation. So, what I did in that lecture, and I don't want to repeat it actually, I expressed every variable in terms of P. Q is already expressed, because V is a constant. Now here, these two, the easiest way to do it is add 2 variables, and I will have Q equals RC square, right? If you add, PC will eliminate each other. This will be 2Q and 2RC square. And since I know how the Q is expressed in terms of P, I know R. Now, if I subtract, I will have similarly for S. So, I have expressed PQ, in terms of P, I have expressed Q, R, and S, then substituted to this, I can get P, and then from P I can get all the rest of this. So, that's one of the examples when it's really kind of a simple thing to do. Now, what if you don't have this particular type of a system of equations, which you know basically how to do? There is a standard approach, so to speak. Well, again, it's just your ingenuity and certain things you can come up with, and the more you solve different equations, finding these peculiarities which you can use to solve it, the richer will be your vocabulary, your repertoire of how to approach different problems. So let me just present you a couple of examples which probably might help you. Okay, this is the first one. Okay. Both equations are really quadratic equations of second degree. This is second degree because everything is square, and this is also second degree because 1 and 1 multiplied together, and we are summing the powers. So it's not so easy, right? Well, let's think about it. Let me try to do the substitution. Maybe it will work. First of all, I have to observe that x not equal to 0 and y is not equal to 0, because otherwise their product would not be equal to 6. If that is true, then I can express y in terms of x from this particular thing. I divide by y, left and right. So I will have x equals to 6, and I can divide by divide by x. So I have y on the left and 6 over x on the right. And x is not equal to 0, so this is fine, no problem. And then I can substitute this into the first equation. So what do I have? X squared plus 36x squared equals 13. Okay? What is this equation? Well, it's not quadratic, that's for sure. Well, let's do something about this equation. I will multiply by x squared, both parts. I will have x to the 4th plus 36 equals 13x squared, or x to the 4th minus 13x squared plus 36 equals to 0. Okay? Now, this is an equation of the 4th degree. But if you remember, in lectures dedicated to high-order equations of one variable, this is a special case. But see, what's special about this? Well, this is the 4th degree polynomial. However, there are only 4th and the 2nd degree here, which means if I will have a new variable z, which is equal to x squared, then x to the fourth will be z squared minus 13z plus 36 equals to 0. And this is a square. This is a quadratic equation, right? So we can solve it for z. Whatever the solution will be, I will have two solutions. 13 plus minus square root 169 minus 4, 120, 144. Is that right? Divided by 2. So this is 25, so it's 5. Divided by 2, so it's 9 and 4. Okay, so roots of this equation are 9 and 4. Now this is x squared. In case of 9, x might be equal plus or minus 3. In case of 4, x is equal plus and minus 2. Now, since y is equal, as you remember, this, so I have 4 different solutions to my quadratic equations. 3 and 6 divided by 3, which is 2. This is one pair. Second, minus 3, 6 divided by minus 3, it's minus 2. So it's minus 3, minus 2. Now, if it's 2, it would be 2 and 3. And if it's minus 2, it will be minus 2, minus 3. So these are 4 pairs. Each pair is a solution. By the way, if you see these are very symmetrical relatively to exchange of the places between x and y, and the solutions are symmetrical. I have 3, 2, and I have 2, 3. I have minus 3, 2, and minus 2, minus 2, minus 3. So solutions are also symmetrical, which basically kind of agrees with whatever we feel is supposed to be. Now, obviously, we can just check each one of them. Well, let's say this one, minus 3, minus 2. Minus 3 squared is 9, minus 2 squared is 4, so sum is 13, and the product is 6. So basically the checking is working, and you can check every one of those. So this is an example of how well, non-trivial, if you wish, case can still be resolved. So in this particular case, we used substitution from this to this. As a result, we had an equation of the 4th degree, but the good equation of the 4th degree, which we can solve using the substitution z is equal to x squared. All right. And one more example. This is basically an introductory lecture about quadratic equations. It needs a lot more of examples with solutions, which I do intend actually to provide in other lectures dedicated to this topic. But since this is just about basically definitions and basic properties and basic approaches to quadratic equations, I will restrict myself to only one more example. And here it is. X squared plus y squared plus z squared equals to 29. Xy equals to 6. And x plus y plus z equals to 9. Well, again, this is not exactly the system which we can solve blindly using some approach, because I have 2 equations of the 2nd degree and 1 equation of the 1st degree. However, I might actually try to do something about it. Now, what can be done? Well, what can be done? Here is what I might actually suggest. Why don't we multiply this by 2? I will have 2xy equals 12. And I will add it to the 1st equation. So I will have x squared plus 2xy plus y squared plus z squared. 2xy I inserted in between these equals to 41. Now, what is this? Well, this is obviously x plus y squared plus z squared equals to 41. And let me rewrite the bottom, but I will put parentheses around it. Now, what's interesting about this system? Well, if I will put x plus y is equal to u, some kind of an intermediary variable, I will have a system which is u squared plus z squared equals to 41. And u plus z equals to 9. This is much easier. This is a system of two equations with two variables. Granted, it's quadratic equation, but only one of them is really quadratic, another is linear. Which means what? Which means we can very easily solve it using the substitution. So u would be equal to 9 minus z, u squared would be equal to 81 minus 18 z plus z squared plus another z squared equals to 41. 2z squared minus 18z plus 81, 41 plus 40 equals to 0, reduced by 2, z squared minus 9z plus 20 equals to 0. Well, this is quadratic equation. We can very easily solve it. I mean, I just see that roots are 4 and 5. So u is equal to, z is equal to 4 or 5. All right, that's much easier. Now we can substitute it to, let's say, this and this, and basically, or actually we can use this one and this one, doesn't really matter. Okay, so let's do it. We don't need this anymore. So we'll use it here. So let's say case number 1, z is equal to 4, and I will consider only these two. So xy is equal to 6, x plus y is equal to 5. Well, this is again, substitute y is equal to 5 minus x, put it into the first equation, and I will have minus x squared plus 5x equals to 6. Am I right? Or x squared minus 5x plus 6 is equal to 0. X is equal to 2 or 3. And y is equal to 3 or 2. So, what we have right now is, that's very important not to lose our ends. We have z is equal to 4, and x is equal to 2, and y is equal to 3, or 3, 2, 4. That's what we have in this case. That's number 1. Number 2, when z is equal to 5. Now, same thing here. I have xy is equal to 6, x plus y is equal to 4. So, y is equal to 4 minus x from here. Substitute to this would be minus x squared plus 4x equals 6, or x squared minus 4x plus 6 equals to 0. And this doesn't have any solutions because 4 squared minus, which is 16, minus 4 times 6, which is 24, is negative, so you will have negative under the square root. So no solutions here. So the whole system has only these two triplets of x, y, and z as solutions. And if you can substitute it, you can definitely see that the checking works as well. All right, great. Now, I do recommend you to read notes to this particular lecture. It's on unizor.com in the Algebra section. It's called System of Quadratic Equations. Now, I do plan to provide more examples of different systems of quadratic equations with non-trivial approaches how to solve them. And again, what's very important is the more problem you will solve, or you will listen to how I'm solving and then you will try it yourself, the richer will be your repertoire of techniques which you can use. And that's why what I was talking about as ingenuity would actually be much easier for you. You don't really have to invent something. It will be already inculcated into your minds that you can try this way, you can try that way. It's easier to, well, invent, quote unquote, something if you had something similar in the past. That's it for today. Thank you very much.